Good morning, everyone. Uh, Today we're going to finish up on lecture 5. We still have about 20 slides to go, so not a lot, but it is, complicated, as I said, right, for this particular topic. So afterwards, we can maybe take up some questions from the study guide to sort of help you as a refresher, as a review. But so far, let's do a quick recap on what exactly is happening so far. Right. So we know a couple of things, right? We know cellular respiration. Cellular respiration is a redox reaction. And what that means is it involves transfer of electron from one reactant to another. So, do you remember which reactant is the one that is being reduced? Which reactant is being reduced in this reaction? Now, if you didn't know that, that is an important thing to know. Okay, so let's go back to our study guide here. Maybe we should write it down one more time. So the word equation is glucose plus oxygen, which produces carbon dioxide plus water, right? And ATP. The chemical equation is glucose, C6H12O6, plus 6 oxygen. That produces 6 carbon dioxide plus 6 water and 36 ATP. And you should know by now that the glucose is the one that is going to be oxidized. Okay, this thing is for the chart below. I'm going to just move it there so there's no confusion. That's the one that is going to be oxidized, right? And the oxygen is the one that is going to be reduced. Okay. So what that means is we are removing electrons from glucose, and we continuously harness energy from glucose. Right? There are two ways we can extract the energy from glucose. Right? We can directly create ATP from it, and that happens in the first step, glycolysis, as well as the Krebs cycle, right? So that's called SLP, substrate level phosphorylation, where the enzyme is going to basically remove a phosphate from the donor and put it onto ATP. Okay, so we are harnessing ATP directly from the glucose molecule as it is being broken down. The second way we can make ATP from glucose is to remove electrons from it. Okay? But we need to take those electrons to the last step, to the ETC, right, to the electron transport chain. And then we will use the oxidative phosphorylation to make the ATP at the end. Okay, so let me write that down for you. As glucose is being broken down, right? High energy electrons are released and captured by energy carrier like NAD plus and FAD. These electrons will be taken to the ETC, the electron transport chain, where their energy are used to create ATP by the method is called oxidative, right? Phosphorylation. Okay. Remember, a majority of the ATPs are produced using oxidative phosphorylation. Okay, so ATP can also be produced directly as the glucose is being broken down by substrate level phosphorylation. So by the end of the Krebs cycle, and we have produced some ATP so far, right? I don't know if you guys remember. How many have we produced by the end of Krebs cycle? Do you want to take a look at the chart that we wrote last time and tell me how many? 18 is a bit much. Oh, okay, I see what you mean. Like, but I mean like directly, right? Directly producing ATP using substrate level phosphorylation. Okay, so let's take a look here. Right. So we got 2 from glycolysis, and we have 2 from Krebs cycle, right? So 4. Okay, 2 from glycolysis, 2 from Krebs cycle. Right. So by the end of the Krebs cycle, we have produced some ATP, 4 net. Okay, and a lot of NADH and FADH2. Right. I don't know if we should put S on them. It's just like a lot of them. Right. Again, we got these NADH and FADH2 because we are capturing all the electrons that are released as glucose is being oxidized. Does anyone have any question about what's going on so far? Like, or about any of the things that I've written? You really gotta have a good understanding of the situation before I teach you the next part. Otherwise, it's just gonna be like even more confusing, right? And I guess I've been busy for the past couple of days, preparing for tests and quizzes and stuff like that. You might not have enough time to go through the notes, but off the top of your head, anything I can help you with. All right. So that's the first 3 steps: glycolysis, pyruvyl oxidation, Krebs cycle. Now I'm gonna tell you what happens in the ETC. Okay. Electron transport chain. Okay. The ETC. Now, if you have a new piece of paper, you probably want to use it. Like if you have been writing notes, if you have been writing notes like that, and now you have just half a page, probably not big enough for what we're gonna do. All right, you might want to start a new page. So I'm gonna draw a line here. Okay. That is the outer mitochondrial membrane. And this is like cytoplasm out here. Cytoplasm. What is this wavy thing that I just drew here? Anybody know what that represents? A lot of you say matrix. The matrix is in here. And this is the matrix. Okay, so yeah, this would be the inner membrane. Which folds up into the cristae, right? Hey, remember the mitochondria I always draw like this? We're basically zooming in here, right? How about here? What is this location between the outer and the inner membrane? Anybody remember what that location is called? That's all right. That is the intermembrane space. Okay, so we got the outer membrane. We have the inner membrane that's folded up into this cristae. And the space between the two layers is called the intermembrane space. And then the innermost portion of the mitochondria, as you know, is called the matrix. Any question about the picture? Do you know what we are looking at here? Just zooming in into the mitochondria, okay? So where is the ETC? Where's the ETC? Well, the ETC is actually a series of proteins that are embedded in the cristae. So there is an ETC. And then you would have like, another ETC here. There's like thousands of them. That's why you want to fold up the inner membrane. The more surface area you have, the more ETC you can pack into it, right? So this here is an electron transport chain. Now, I'm not going to write too many description here. I'm not going to ask you to describe it on the test, okay? But like all the things I'm explaining to you is written out in the PowerPoint slides, okay? Like all the things I'm going to tell you, it's all written out in the PowerPoints, okay? So there's no need. Like I mean, you should go back and read about it afterwards, okay? But I'll just explain to you what happens here. Hormones, ETC is channeled. Sort of. They're kind of like pumps, as you will see. Okay. All right. So these are ETC, okay, electron transport chain. So what happens is this. you know, all those NADH and FADH2 that we produced, right? What they will do is they will come to the first protein in the ETC. All right, so I'm going to write here, we're going to have an NADH, and the NADH will release the electron will get off, right? And it will go back to the NAD plus form. Right? So NADH is going to be oxidized into NAD plus. When you lose electron, you become oxidized. So the electron is going to hop on here. Let me choose a color that actually will show up. I don't know. I think maybe green. Does green show up? There we go. Okay. The electron is going to get off from the taxi, right? Get off from the NADH, and then it gets loaded onto the first protein in the ETC. Okay. Maybe I can write it down for you. Let me silence my phone so it doesn't bother us. Over here, let's go back here for a second. Right? The electron transport chain is basically a group of membrane proteins found in the cristae. Okay? And again, you have like thousands of these ETC embedded throughout the inner membrane of the mitochondria. The more ETC you have, the more ATP you can create, you know, ongoing, right?
I have a quick question.
Yes, please.
So as like the NADH or taxi pulls up to like, I guess it would be like a station. So the person getting off would be the electron. And then when it comes back as NADH plus, that would be like the empty taxi kind of thing.
That's right. Why don't you tell me, where will the NAD plus go next?
Back to the first place. I can't remember the name of it.
You got it, right? We'll go back to like either step 1, step 2, or step 3
Yeah.
to pick up more passengers, right? Pick up more electrons so they can drop them off.
Okay. Okay. Thank you.
Good. Anyone else? All right. I hope I'm making sense here. Let's go on. So we have, you know, a bunch of proteins in the ETC, in the transport chain, right? So the electron gets on, and it's like a game of hot potato. If you don't know what that is, it's basically, imagine, I give you a hot potato. It's so hot you can't hang on to it, right? So you pass it on to the next person. The next person catches it. It's so hot they cannot hang on to it too much, and then they pass it on, right? So the electron gets on in the first protein, and then it will pass it on to the next. Oops, wrong color. It will pass on to the next, and then it will pass it on to the next. Okay? Just boom, 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 one on to the next. Now remember, these electrons are full of energy. Okay? So as they are being passed on, we want to harness some of those energy. We want to use some of those energy. To do what? Well, we are going to use those energy to pump hydrogen ion, H+, from the matrix into the intermembrane space. Now, hold on a second. You are like, wait, where do the H+ came from, right? Well, I didn't really go into all the details with you, but you can kind of understand, right? Look, NADH, the H is the hydrogen, right? So when they let the electron off, when they became NAD plus again, there's going to be a H that's given off, right? So some of those H plus will be pumped from the matrix to the intermembrane space. So, yeah, go ahead, please.
So the H plus comes from the purple dots, which are the ETC. So the
Oh
hydrogen.
no, hold on, hold on. The H plus doesn't come from the purple circles, okay? They came
Okay.
from, you know, the NADH here, when it becomes NAD plus again,
Mhm.
they're gonna have an H plus as well, right? Because that's where the H is, right? So now
Okay.
you would just have a bunch of H plus floating around in the matrix, and then we
Okay.
want to pump them from the matrix to the intermembrane space.
So how are they pumped to the intermembrane space?
That's why we need the electrons, right? Now,
Okay.
the electron is full of energy, so we use that energy to basically pump them. Now, why do we need to supply energy to pump things? Well, earlier in lecture 4, we learned about active transport, right? That is going from low concentration to high concentration. Now you can imagine this. As we keep on pumping H plus from the matrix into the intermembrane space, you are going to ultimately end up having high H plus concentration here, right? Because they keep on coming in, right? And over here, because we keep on getting them over to the other side, we would have low H plus here. So in this case, the ETC is working against the concentration gradient from an area that's low to high. And that's why it needs some energy, okay? But we don't want to use ATP to supply this. We actually try to make ATP in the process, right? So instead, we are using the energy from those high energy electrons, right? We harness the energy from the electron and then we use it to pump H plus from matrix to intermembrane space. Okay, so I said a lot of things. All right. Any questions at all? Okay, I have a question for you then. All right. And I hope, you know, everybody can answer this. The yeah, good morning to you too. The H plus, okay? Where do you think the H plus wants to go? Look, it's high concentration in the intermembrane space and low H plus in the matrix. So if you stop the pump for a second, if you stop the ETC for a second, which way would the H plus want to go naturally? Do they want to go to the matrix or do they want to go to an intermembrane space? What's the natural path of H plus if we stop pumping them for a second? Okay. Medicine say matrix. Anyone else in the Kiana said inner membrane, but inner membrane is a barrier, right? So like I mean like you can't go into the inner membrane. Ramon said matrix because it's low concentration. Yeah, that's correct, right? So let's put all those together. What the H plus wants to do is to go from intermembrane space back into the matrix, right? Because things naturally wants to go from high concentration to low concentration, right? But it actually cannot do that because the inner membrane is acting as a barrier, right? The inner membrane is also made of the same stuff that makes up the cell membrane. So it doesn't let charged particle to go through, right? So all these H plus is building up and they really want to come down, but they can't because the barrier, the inner membrane is blocking them. Okay? Now don't write this. I'm just trying to help you understand it. It's sort of like this. You got a river, sorry, not river. What do you call this thing? Waterfall. Sorry, waterfall. Okay, so the waterfall, all this water is coming. Okay, lots of energy, just like dumping down, right? Okay, from area of high height to low height, right? It's just naturally coming down. And then what we want to do now is we actually put a barrier here. We put a barrier here. So that shuts off the waterfall, and then the water is building up, right? Building up. It's building up like this. Right? So now we have a reservoir of water. It's really, really built up. It really wants to come down, but the barrier is in the way. So how do I let the water through? What do? We're gonna have to give it like a a special, like a little hole here. And then as soon as the hole is available, it just like comes right through. Right? And then what we can do is we can put like a turbine here. And then the turbine will basically turn and use all those water energy to create electricity, right? I mean, that's what happens in a dam, right? You dam the water and then you use the water to generate electricity. Okay. Now, what does this have to do with any of the stuff that we talked about? Let's go back to this situation here, right? Look, we created a lot of H plus here. That's like the water banged up in the dam. They want to come in, but they can't because there's a barrier, right? So like we block it. So how do they come back in? Well, there is a special protein. Okay? The special protein looks like this. It looks like a doorknob. Okay. And you have, again, thousands of these things throughout the cell membrane. The inner membrane. Okay. This guy is called ATPase. Sometimes the textbook will also say ATP synthase. Doesn't matter. Same thing for us. All right. And this is like the turbine. This is like the turbine. It provides a way for the H plus. It provides a way for the H plus to go through and come back in. Okay. As the H plus comes back in, it literally turns the ATPase, okay, and that allows ADP and P to become ATP. Okay. So that's what I described to you just now. That's oxidative phosphorylation. What's driving the phosphorylation? What's driving the production of ATP is essentially the electrons, right? And the electrons were created from oxidation. So that's why it's called oxidative phosphorylation.
Sorry, I have a quick question.
Mm-hmm.
So as the H plus comes back into the matrix, it's generating energy to form the ATP.
That's right. So as it's coming back down, much like the water is falling, going through the turbine, right?
Okay.
Instead of converting it to electricity, we're converting it into chemical energy. We're converting it into ATP.
Okay, so where does the ADP come from in the first place?
Well, they could be anywhere, right? Every time you use up an ATP, you regenerate the ADP, right?
Okay.
Right. So like, when you move the muscle, when you do transport work, when you do whatever, right? You just have ADP is like a bunch of spent battery, right? They need to be recharged, right? So they're just kind of all over the cell, right?
Okay.
All right, I have a question for you guys again. So how many ATPs can we create from these H plus? What do you think, huh? What did I say?
Was it one each?
So a total of how many?
Two, right?
Is it two? How
Or
do
is
you
it a total of one?
You said one each, so
So
how
it'd be
many?
total of one.
So how many total of what? How many?
So it'd be total of one because each ADP gets one ATP, or am I wrong?
Oh, I think we just have a miscommunication here.
Okay.
So the question is the H plus, right? The H plus is gonna go through and it's gonna create ATP, right? So my question is how many ATP can we produce from here? Anyone else? You guys are awfully quiet. Forgot, that's okay. Anyone remember? No, no, no. Uh-oh. Well, let's go back a little bit, guys. The H plus were pumped using electrons that were captured by NADH. How many ATP can NADH produce? You must remember that, right? No? 3. Okay, 3. If you don't remember, let's go back here. Where is it? All right, each NADH carries enough energy to make 3 ATP, right? and then each FADH2 carries enough energy to make 2 ATP. So in this case, the NADH lets the electron off. It's going to get passed through. It pumps enough H plus over so that when they come back in, you will create 3 ATP. Okay. Any question? All right. Let's read the words. This is basically what I've described to you. It's in the PowerPoint. You can read it yourself later, but I'll read it to you once. NADH and FADH2, remember, these were generated from glycolysis, pyruvate oxidation, and Krebs cycle, right? So they took the electron and then they will go to the ETC and deposit the high energy electron onto the ETC, those purple circles, right? Those are membrane proteins in the cristae. As the electron are passed down the ETC, right, one onto the next, onto the next, it loses energy, right? And that energy is used to pump H plus from the matrix to the inner membrane space. The concentration of H plus increases within the intermembrane space, okay? They really want to come back into the matrix from high to low, but they cannot because they are charged, okay? So they cannot simply diffuse back across the membrane. The only way back in is through the ATP synthase, that orange doorknob looking thing, right? And when they do go through the ATPase, the energy that is built up from the concentration gradient is captured to produce ATP. Now, what's missing in my picture, huh? Anybody know what's missing in my picture here? That's right, we're missing the FAD. We're missing the FAD. Right? So FAD, because it contains less energy, instead of hopping on at the highest level, at the first protein in the ETC, the FAD is going to hop on here in the second one. Okay, FADH2, I should say. And then it's going to become FAD. Right? So it will also let the electron get off, but because it got on at a lower level, it's not going to be able to pump as many H plus over, right? And as such, when the H plus goes back into the matrix, you will only be able to create 2 ATPs instead of 3. All right. Now, there is just one final thing here. Let's go back to here. Is there a question? I heard someone said something. Nope. Okay. Let's think about this for a second. All right. So at the park, when I take my kids to the park, sometimes I get really annoyed. Not by my kids, okay, but like, someone else's kids. So here's the slide, right? Every now and then there is the kid that slide down the slide, and then they stay at the bottom for whatever reason. Okay, they just sit there oblivious about the surrounding, and then not going anywhere, right? So I always tell my kids, don't slide down when there is someone else at the bottom. You're gonna hurt the guy, okay? So then my kid is sitting up there not happy because the other person is not gonna go, right? So what happens is there's gonna be a parent that come around, right, and then pull the kid out, right, from the slide so that the next one can go, right? So remember this, story when you think about the ETC. Right? The ETC is like a slide, okay? More like a stairs, if you would. The electron hops on and then it goes boing boing down the ETC, right? The electron transport chain. But when it gets to the bottom, it's like that kid that doesn't go away, right? It stays there. And until it moves away, the next electron is not gonna go. Right? The next electron is not gonna come down, right? So we need to have something. We need to have a parent to get that electron off. And that parent, right, that molecule is going to be oxygen. Right? So oxygen is called the final electron acceptor. Okay? Its job is to pull the electron off, and in doing so, it becomes water. Okay? And where does the H come from? Well, don't worry. There's lots of H floating around. We know that already, right, in the matrix. Right? So if you think back to our equation, I'll come back to this for you to copy in a bit, but if you go back to this equation that we wrote, right, cellular respiration is a redox reaction. We got the electron off from glucose. Ultimately, where do they go? Well, after being carried by the NADH and the FADH2, ultimately those electrons will end up on the oxygen, right? When the electron gets on the oxygen, they become the water, right? So oxygen is the final destination of all those electrons. By the time they get to oxygen, they don't have energy left anymore. We use their energy. What did we use it for? We use it to pump H plus from the matrix to the intermembrane space, right? To create that reservoir, to create that gradient of H plus so that we can make ATP from it, right? And so at the end here, I'm just going to add to our picture here, there's going to be O2, and then it's going to get converted into H2O. Does this make sense? So that's why we have to breathe, right? If we don't breathe, if we don't have enough oxygen in the body, then the ETC is going to get clogged out, right? Without the final electron acceptor, without the oxygen, the ETC is not going to flow. The electron does not get passed down. If the electron does not get passed down, we cannot pump H plus from matrix to intermembrane space. If we're not pumping H plus over, we are not creating the concentration gradient. Without the gradient, H plus will not go through ATPase. That's like not having water going through your turbine. You're not generating electricity. In this case, not having H plus go through the turbine, the ATPase, we are not producing ATP. Without ATP, you die, right? Your heart cannot beat without ATP, right? And so that's why oxygen is essential.
I have a quick question.
Yeah.
So in the end, there's going to be like H2O or water like hanging out in the matrix, or
That's right. So like matrix is mostly water anyways, right? But you know, some of this water might go back to the cytoplasm, some of it might even go to your bloodstream, and it just becomes part of our blood ultimately.
okay.
All right. So no questions at all. Now, one last concept I want to talk about here. There is something called electronegativity. Did you guys learn this in chemistry yet? Electronegativity? No? Okay. So what is electronegativity? Electronegativity is the attraction for electron. Okay. High electronegativity equals high attraction for electron. If something has very high electronegativity, then it absolutely loves electron. It's gonna wanna hang on to it. Okay, it want to hang on to it. So let's see. Okay, see if you can understand this. Let's say this is 1, 2, 3, and 4. In this arrangement, the 3 membrane protein and then the oxygen, which one has the highest electronegativity? Let's do a poll here. Okay. Which one do you think has the highest electronegativity? Yeah, A, B, C, or D? Right? A, B, C, D. I should have said A, B, C, D. A, B, C, or D? Which one has the highest electronegativity? Hmm. Okay, I got some response, and looks like people are getting it backwards, which is fine. That's why we should talk about this. So it turns out the highest electronegativity is the oxygen. Highest electronegativity. Look, if the first one has the highest love for electron, then as soon as the electron gets on the first one, it's gonna hang on to it, right? It's like, I'm not gonna give this electron away. I love it so much. Okay. Number two, like B wants it. Nope, too bad. I have high electronegativity. I'm gonna hang on to it, right? And if that's the case, then nothing will ever flow, right? Okay. So the fact that the next one in the chain has higher electronegativity means they could grab it, right? They could take it from the previous one. And then the next guy will grab it from the next one. And that's how it's able to flow, right? So B has higher attraction for electron than A, C has higher attraction for B, and then oxygen has higher attraction for C. Think of it as a series of magnets that are increasing in strength, right? So as soon as you put like a little metal ball here, it gets sucked to the next one. It gets sucked to the next one, and then ultimately it gets picked up by oxygen. Okay, so keep this in mind, because we are gonna come back to it in a few slides. But that's pretty much it for the time being. All right. Now I want to go back to this table. I want to go back to go to this table. This is question 4 in the what do you call this thing? The study guide. Yeah, so I'm going to give you a moment to pull that up, and I'm going to fill this table in for you to show you where the 36 ATP comes from. Okay, so hopefully after this, it will make more sense. Okay. Now on the test, I try to keep the questions really simple for this lesson, okay? For lesson 5, lecture 5, because I know it's really complicated. So I'm not going to ask you really obscure things. I try to keep the question as obvious as possible, okay? Hopefully that will help you. And if you really hate the like the written questions, the ones you have to type it out, then rejoice, because there's no written questions for the test. All right, they're all going to be just multiple choice and multi-select. Do you guys have a better time this time around for quiz 2? In terms of like, did you guys have enough time this time, or like it was still a little bit rushed? Some of you still didn't answer the long answer questions. So I don't know. Anyway, let me know what you think if you want. So here we go. Glycolysis, right? Number of ATP through substrate level phosphorylation, right? So we know there is 2 net ATP, right? 2 ATP. This is net. And energy carrier, how many do we produce? What kind and how many? Yeah, we have 2 NADH. That's right. 2 NADH. Now there is a little bit of a catch here. Okay, let me put a star here. These are produced in the cytoplasm, right? Because of course you know glycolysis happens in cytoplasm, right? These are in the cytoplasm. And they need to go to the ETC, which is in the cristae, right? But it turns out NADH is too big to cross the cell membrane. All right, so I'm going to go back to this picture here to show you. All right, you don't have to necessarily draw it, okay? But from glycolysis, we have the NADH, right? We have 2 NADH. Okay? But these are too big. It's not able to cross 2 layers of membranes, okay? Because it needs to cross the outer membrane and then the inner membrane and then drop the electron there, right? Okay, but it cannot do that. So instead of the NADH crossing, they will just let the electron cross. Okay, they will just let the electron cross, and then this will become NAD plus again. But something else has to pick up the electron and take them to the ETC, right? Okay, so that would be the job of FAD. They'll pick it up, and then it becomes FADH2, and then it will go over here. All right, so there's an extra step here. Now you might think, hey, why? How come we don't use an NAD to pick this up? Right? I mean, it was NADH before. Why don't we keep it the same? Why do we have to do FAD? Well, remember, whenever there is an energy transfer, it's never 100% transfer of energy, right? You always lose some energy, right? It's law of conservation of energy. Like you will always lose a little bit in the transition, right? So when the electron goes through, it loses some energy, so it's not as energized as before. So it's only worth 2 ATP now instead of 3. Okay, so that is only a problem for the NADH that are producing glycolysis. All the other NADH were producing the matrix, right? So they don't have to go through this extra step. Okay, so over here, the 2 NADH, right? These are produced in the cytoplasm and cannot go to the ETC directly. Right? So instead, what happens? Well, instead, these are gonna get not converted into FADH2, but then they pass the electron to the FADH2 in the matrix. Okay. And then this would be used to pump H plus and create ATP. So how many ATPs are produced? Well, 2 FADH2 multiplied by 2 equals to 4 ATP. Okay. So this is oxidative phosphorylation, right? Over here, that's substrate level phosphorylation. ATP at the ETC, that's called oxidative phosphorylation. So together, 4 plus 2 gives you 6 ATP.
So for the ATP produced at ETC is the oxidative phosphorylation?
Sorry, I didn't hear the first part of your question.
So ATP produced at the ETC is like the same thing as oxidative phosphorylation?
That's right. Yeah, so the method that is being used is called oxidative phosphorylation. Right? Okay. Because it's driven by the oxidation reaction. Right? Those electrons, right, came from oxidation. Can you try to fill in the second row here? Please just take a moment. Try your best. And I'll give you like 3 minutes to do it. And then I'll take it off. All right. How many ATPs are produced through substrate level phosphorylation in pyruvate oxidation? First of all, this happens in matrix. But how many ATP, guys? Please tell me the answer. All right, we'll do a poll. Even doing a poll is like hard to get you guys to respond. Is it 0? Is it 2? Is it 4? Is it 6? What do you think, huh? I got 5 answers. Where is the rest of the class? Oh no, only one only one person got it right. That's a little bit unfortunate. Now, where do you find the answer? Let's go back here. To the previous chart. Pyruvate oxidation. What are the main products? Carbon dioxide, NADH, and 2-acetyl-CoA. Do we see any ATPs here? Absolutely not. Okay. So how many ATPs do we have through substrate level phosphorylation? 0, nothing, nada. Okay. How about energy carrier? Right. Okay, say 2 NADH, that's correct. Now, do these need special treatment? Nope, they are already in the matrix, right? They don't have to smuggle the electron through the 2 layers of barrier, right? Okay, they just go right to ETC. So we're just gonna take 2 NADH, and what do we multiply by this time? Well, we don't multiply by 0. What do we multiply by for NADH? 3, that is correct, because each NADH has enough energy to produce 3 ATPs, right? Okay, so that is going to be 6 ATP. And when we add them up, 6 plus 0 is 6 ATP, right? All right, let's keep going. I'm hoping the enthusiasm will will give you some motivation. All right, last row here, Krebs cycle. Hopefully you know where to find the answers now. I'll give you another 2 minutes or so to write them out. Okay, how many ATP through substrate level phosphorylation from Krebs cycle? Yeah, okay, one per spin, right? Okay, so that's two in total. Right, let me go back to yesterday. Last class notes, right? Hold on. Got way too many things open here. See, glucose become 2-pyruvate, and then 2-acetyl-CoA, and each of them will do a spin, and then you have one ATP here, 2 ATPs, right? Where was I? So 2 ATP from substrate level phosphorylation. Good. Energy carrier. How many NADH here? How many NADH? 6. That's right. And 2 FADH2, right? We are already in the matrix. We're ready to party. This is going to be 6 NADH times 3. Always times 3 for NADH. That gives you 18 ATP, right? And 2 FADH2 times 2, that gives me 4 ATP, right? So 18 plus 4 plus 2 is 24, right? 24. So 6 plus 6 plus 24, 36.
Sorry, where did the +2 come from in the ATP produced?
Oh, why is it 18 plus 4 plus 2? Is that your question?
Yeah.
Yeah, this column, right? The 2.
Oh, yeah, okay.
Yeah. So we group everything together. So that's how we get our magic number 36, okay? Now, of the 36, 4 of them are produced by substrate level phosphorylation, right? So what's 4 divided by 36 times 100? Huh? Take your calculator out, plug that in for me. 4 over 36 times 100. So exciting. It should give you goosebumps when you see the number. Anybody?
Sir, you mind saying that again?
Oh, sorry. I got too excited myself. No, I'm just saying, right? 4 out of the 36 ATPs, right, are produced through substrate level phosphorylation. So I want you to key in 4 over 36 times 100, right?
Oh, okay.
Yeah. So 11.11%, right? What did I tell you last time? What did I tell you? I was like, I think I told you. Where is this? Right? Only about 10% of the ATP are produced this way, right? Right? To be precise, is 11%, but 11.11111 is a hard number to remember, right? So that's why I just round it down and say 10%. But now you know, right? Not a lot of ATP are produced through substrate level phosphorylation. It's not a common method, right? Most of the ATP, in fact, the remaining 32 ATPs are produced by oxidative phosphorylation. All right? There you have it, the hardest lesson of Unit 1. We've done the hardest part now, okay? We still have a little bit, extra things to talk about after the break. But as far as, the different steps, different stages of ETC, that's it. Okay? Yeah, I know this is crazy hard. I hate teaching it because everybody just gets really overwhelmed. But like I said, I honestly make the quiz, the test questions for this lecture very straightforward. Okay, like I'm not gonna ask you like obscure things. It's just things that we've been talking about over and over again. Right. So like I said, right? If you spin the Krebs cycle 4 times, how many ATPs are you gonna get? Right. So things like that, right? Or I can ask you, substrate level phosphorylation occurs in which steps of the cellular respiration? So it's only in glycolysis and only in Krebs cycle. So you still need to know the things, but at least you won't have to explain the concept, right? Okay, like I'm not going to ask you to describe, oxidative phosphorylation, right? I'm going to do that for my in-person class, but in an online environment, at least you don't have to explain that. Okay. I mean, the class average was not bad. It's half decent compared to the first one. First one was a little bit. I think it was higher, right, for the second time around. And most of you did, relatively well, and some of you did much better compared to the first quiz. So yeah, hopefully you guys can continue this trend. We are losing a lot of people in class though, right? I remember at the beginning we have like 30 people coming to class, and now we only have like 18. But you guys are the one that comes, so well done. Let's have a quick break. I will come back in 9:40. Okay, and then we'll do more. See you in a bit.
We've had 30 people in this class.
We still have 30 people. We actually have 35 people in the class, but then only like at the beginning we had 30 people who showed up for these live sessions. Now we're down to 18. I don't know. I'm doing my best here, but I guess my my enthusiasm is not enough to attract people to come. But whatever, it's okay. Yeah, I'm not too bummed about it. All right, see you guys in a bit. Hello, let's keep going. Now, like I said, the hard part is over, so I'm gonna switch back to the PowerPoint slides. Probably should have warned you that before the break, so you can pull it up. It will give you a moment to get that, and I'm just gonna go through the rest of the slides for the lesson. Now, as you are pulling the slides, I'm just gonna bring you up to speed here. For the rest of the class, we're going to look at some disruption of oxidative phosphorylation. And that basically is what's happening in the ETC, in the electron transport chain, right? So we now know oxidative phosphorylation basically involves two key events, okay? We have to create the H plus gradient by constantly pumping H plus over into the intermembrane space. Okay, so creating a gradient is the first step, and then letting the H plus go through the ATPase, that would be the second step, right? As it's coming back down, coming back in, we use those energy to make ATP. Right? So there's two phases to it: generating the gradient, creating the damp, and then letting it flow back. So there are several poison, I guess, that can obstruct this process, and it could interfere with it in one of few ways. Number one, it could block the ETC, right? So I'll explain more in a bit, but if you block the ETC, the electrons can flow, and if it doesn't flow, then you don't generate the damp, right? You don't generate the gradient. No ATP, we die. Next one, inhibit the ATP synthase, right? That's the orange doorknob thing, right? The turbine, right? I keep on calling it. If you block the turbine, H plus don't come back in, we don't create ATP, we die. Number three, you can make the membrane leaky. That's the crystate, right? So if you make that leaky, like let me show you the picture again, right? The whole process relies on the fact that we have a barrier. So that we want the H plus to go through the turbine only and not anywhere else. But if you make the membrane like all leaky, don't do this to your diagram, but if you make it all leaky like this, put a hole here, put a hole here, put a hole here, right? Then the H plus will just leak through the holes. They don't have to go through the turbine. They would just leak right through, right? So you destroy the gradient, and you're not going to be able to make ATP. And what's the end result? We die, right? So these poisons are not good. Any poison that disrupts the oxidative phosphorylation, right, disrupt the process of making ATP, it's deadly, okay? Because without ATP, we cannot function as an organism, unfortunately. So let's take a closer look at the first set of poisons, okay? The first set is the one that will be blocking the ETC, right? So we have this thing called rotenone, which is used as an insecticide and pesticide, which makes sense. You know, you block the ETC for the insects and the pest, right? I mean, they are animals too, right? So that means they have the same kind of mechanisms in making ATP. Then you kill them, right? Fantastic. It's not so fantastic when it ends up in our food, right? Because you know, if the people use these pesticides for the crops, and then you know they are not cleaned properly, right? Or if the birds eat it and then you know it get passed on in higher up in the food chain, then ultimately it can end up in our food supply, right? So that is not a very good thing. But this one binds to the first protein in ETC and it blocks it. Remember the ETC, the way I've drawn it for you anyways, has 3 purple proteins, right? If you block the first one, right, the NADH comes, but then it cannot put the electron on, right? Look here, right? Like you block this first one, the electron cannot get off, right? The passenger has nowhere to go. So the NADH is stuck there, right? And here's the thing, if all the taxis are stuck with a passenger in it, right? Then we don't have empty taxis to go back for the first 3 steps, right? So eventually you just basically shut down the whole cellular respiration. I mean, you still have some FAD going on here, but that's really small amount, right? You only create 2 FADH2 in Krebs cycle, right? And not anywhere else, right? So by blocking the first protein, we're gonna have a problem. Carbon monoxide. Did you know by law you have to have a carbon monoxide detector at home? Do you guys have one at home? Where do you keep your carbon monoxide detector if you have one? Do you want to tell me where you keep yours? Where should you keep yours?
Then the ceiling, right?
Sure, but like which ceiling? In what location in the house? Or
All of them.
all of them? Okay.
Yeah, a whole bunch, right? I think.
Oh, interesting. Yeah. But usually people should keep them where they sleep, right? In the bedroom, okay? Upstairs. The worst place to keep them is in the kitchen, okay? Because sometimes the people have this smoke detector / carbon monoxide detector thing 2 in 1. And then they put it in the kitchen. But you know, if you cook a lot at home, those fumes from the cooking can actually interfere with how the carbon monoxide detector works. Okay, so carbon monoxide is colorless, odorless, tasteless, right? So you can't see them, you can't smell them, you cannot taste them. Okay, so in other words, you won't know it's there even if it's there. Okay, but where water and carbon monoxide go, you mean the water heater? Yeah, if you live in a house, right? Sometimes your water heater malfunction, and not the water heater, but the furnace. I mean, the furnace malfunction that could produce carbon monoxide, right? Your car generates carbon monoxide. That's why you should never, you know, leave your car on and then you know close all the window and sleep in it or something, right? That's no good. But when the carbon monoxide goes into your body, right, it will bind to hemoglobin and cause hemoglobin to remove oxygen. Okay, so you might recall hemoglobin is the molecule that transports oxygen for you, right? So when given a choice between oxygen and carbon monoxide, it will always bind to carbon monoxide instead. Okay, so it's not delivering oxygen to your ETC. Then without the oxygen, without a final electron acceptor, right? It's like that kid, he's not getting off the slide without the parent. The electron's not getting off without the oxygen. Whole ETC gets clogged, right? No more ATP production. We're doomed, okay? What are some of the symptoms of carbon monoxide poisoning? Do you guys know? How do you know? Like if you don't have a detector at home, and you have some carbon monoxide, you've inhaled some of them. What are the symptoms?
I'm gonna take an educated guess here because
That's good.
said displaces oxygen, therefore removes oxygen, right?
Yeah, yeah,
So
yeah.
what I'm thinking is hypoxia.
Yeah, that's right. Hypoxia basically means like, lack of oxygen, right? And how would you feel when you don't have enough oxygen?
But the thing with hypoxia is that I saw this, the NASA astronauts go through this all the time. They have to go through a hypoxia training just to see what their own symptoms are.
That's
Because
right.
everyone has their own symptoms. I've seen tingling, purple around the nose, euphoria. There's a lot of host of symptoms, but it's different for different people.
That's a good point. Yeah, but that's probably for like really severe kind of hypoxia. But generally we're not exposed to that high level of carbon monoxide. It's just a little bit in the house. You might not pass out just yet, okay? But you're gonna get headache. You're gonna feel tired, and you just like feel sudden onset of lack of energy. And that's why it's so dangerous. Okay, if you don't have a detector at home, what do we normally do when you are home alone, okay, and you feel headache and tired? What do most people do, right? If you're just at home, like you pop a pill, right? Exactly, right? You pop a pill, you take a Tylenol, you take a, Advil, and then you go to sleep, right? And that's how people die from carbon monoxide poisoning, right? Without a detector, right? So like you're supposed to open up all the air and let fresh air come in, right? Leave the place if you could. And that's why you need to have a detector. Okay, so my grandmother, she's really old now. She's like in her 90s, but a couple years back she was home alone and it was winter, and I think it was the furnace at my uncle's place that was malfunctioning a little bit, so there was carbon monoxide coming out. But she was tired. She was like complaining of this headache and stuff like that. And then he called my uncle, and then he said, you know what, just it's probably just the heat. Right? It's too warm in the house. So open some window, right? And then go to sleep or something. That's what she did, right? So good thing she opened the window. If she didn't go open the window and then she went to sleep, it would have been bad. Okay, her hearing is not too good, so she didn't pick up the beep from the detector, which was like in another floor. But anyway, scary story. I went on a tangent. Let's go back to this. Next, cyanide. Okay, you guys know cyanide? If you watch like a spy movie, right? Like James Bond or something like that. Sometimes they say they keep a bit of cyanide, right, hidden, right, in the mouth, right? In case they get captured, they could use the cyanide to basically kill themselves, right? And cyanide is very poisonous. Does anybody know the formula for cyanide? Did you learn that in chemistry class as part of your polyatomic ions? Cn, that's right. That is Cn, negative, right? So cyanide is even more electronegative than oxygen. Okay, remember here? Each protein is more electronegative than the next, right? Okay, so what will happen in the case of cyanide is that the cyanide is going to basically get stuck on the ETC. Okay, and if you have cyanide there, it doesn't even matter that you have oxygen, because then the electron is stuck to the cyanide since it has the highest electronegativity now. Okay, so the electron will not want to get off from the ETC and go to oxygen. Right? It stays there. And like I said many times already, if the electrons don't get off, they don't flow. If they don't flow, we don't make ATP. And you get the point now, right? We die. So these are all things that would interfere with the electron transport chain. Okay, there is another thing called DNP. Okay, DNP. Now DNP was accidentally discovered as a substance that could cause rapid weight loss. Okay, they actually, I think, if I remember the story correctly, they were using this in some kind of factory as like I forgot what it was. I think it was like some kind of stabilizer for paint or something like that. Okay, so then the story goes like this: the person who worked at the factory accidentally ingested some DNP. Okay, from the assembly line, I guess. And then what happens was that he experienced rapid weight loss in the next couple of days. Okay, I don't know how much he ingested. Okay, and then when they found out about this, they were like, "Whoa, this is the jackpot. This is gonna be the best weight loss substance, right? That we can sell to people now, right? Okay, so they didn't really fully understand how it worked, and it turns out what DMP does is it will basically move the H plus across the inner mitochondrial membrane, right? And that's the equivalence of creating holes in the inner membrane. Right? So all these H plus are going through back into the matrix without passing through the ATPase. And if they don't pass through the ATPase, then we're not producing ATP, right? So your body thinks that your metabolism is way down because you're not making all these ATP, right? So your body thinks you are starving. Like what's the problem? Why are we not producing ATP? Are we not getting enough glucose? Okay, maybe we're starving. So let's burn some fat, right? So the body switched to fat metabolism. Okay, now we didn't learn much about fat metabolism, but the thing about burning a lot of fat in a short period of time is that you generate a lot of ketones, okay? And these ketones are acidic, right? So it causes acidosis, right? Causes your blood pH to drop, and that, of course, is not a good thing, okay? So DMP, when consumed continuously, even for a short period of time, is going to lead to heart problems, okay? Rapid weight loss, causing your blood pH to go down significantly, and you could die from it. Okay, so of course, once they found out, they are not selling it as a weight loss thing anymore, but on the dark corners of the internet, people can still get their hands on it. And there are a few people in the US who obtained these DNP and actually died from it, right? And I remember reading a news article, of one of the victims' parents. Right? They want to have tighter regulation for these things. They want crackdown, on internet selling these things because you might try to get lose weight from consuming it, but it could end up killing you very easily. So here it is, right? We can see this is the ETC. I know they have like more purple circles, okay, but I just want to keep it simple. So you have this one, this one, this one. What's the store that sells all these supplements? I guess they have a lot of it, right? A lot of these stores, but like at the mall, sometimes I see like you can buy anything. You can buy vitamin A, vitamin B, you can buy these melatonin and whatever, like a bunch of pills, right? Is it called GNC? Okay. Well, guess what? You can actually buy these ETC proteins as supplements. Okay. It's really bizarre. Right. So this one is called NADH dehydrogenase. You can buy that. There is something called like coenzyme Q, which you can buy it as well. I don't know like if they're actually gonna do anything to you, right? But if you ever want to pump up your ETC production, the pills are there for you. Okay, so rotanin, as I said, blocks the first protein. We have the cyanide and the carbon monoxide disrupting the flow. Right? Cyanide disrupt it because it's very electronegative. Carbon monoxide disrupt it because it blocks the oxygen from getting there. And then the DMP just makes H plus permeable, right, to the cristae essentially. And then the oligomycin, which we didn't go into detail, but it blocks the ATP synthase and it blocks the turbine. All right, so these are just some of the things that could disrupt oxidative phosphorylation. We did this chart already. You can read through it yourself and see if it makes sense. Couple other things. We don't just burn glucose, right? Because our diet is very, should be diverse, right? Like we don't just eat carbs all the time, right? We do eat proteins and fats and stuff like that, and we can break down proteins and fat as fuels. Okay, we just prefer carbohydrates as the main source, but when you break down fat, you know from lecture one, fat is glycerol and fatty acids. So we can break these things down further and feed it into different parts of the cellular respiration. So for fats, you can, like I said, you can break it down into fatty acids, right? So the long chain, the saturated or unsaturated fatty acids, and then you can chop up the fatty acids into two carbons, okay? And each of these two carbons can be converted into acetyl-CoA, and then you would continue onto the Krebs cycle. Okay, like I mean, you don't have to memorize the detail, but the point is you can feed different things into different parts. Right. So here we can have proteins, and depending on which amino acid you have, right, 20 different amino acids. Some you can feed it into glycolysis, some you can feed into pyruvate oxidation or Krebs cycle, right? So it's very versatile. We can have different fuels to use, right? So that's why people like have all these. Like I don't know about the science behind it. Like I'm not sure if all of them are like legitimate, but there are so many different kinds of diets, right? For losing weight, for building muscle and whatnot, right? So you can switch between the different fuels, right? So I don't think there's like a high fat diet out there, right? That is healthy, but you heard about high protein diets, right? You heard about like keto diets. You heard about, just complex carbohydrates rather than simple carbohydrates. So by switching these pathways, right, you basically change your metabolism. You change the way that your body produces fuel, and perhaps it's going to help you, gain some muscle. It's going to help you lose some body fats and so on and so forth. All right, let's take a look at this question. I will put this on the test. Right, so why don't you read it first, and then you can tell me what you think. There are only three choices. Anybody? Okay, I have A, I have B. All right, so this is something that's worth thinking about. All right, so let's draw our thing again. Okay, so you should know by now, because I have been pretty much repeating it whole morning. We have our ETC here, and we are pumping H plus here, right? Pumping H plus. So this is talking about hydrogen cyanide poisoning. So the cyanide will basically bind to the ETC and blocks it, right? And blocks it. So if you're blocking it, we are not pumping the H plus. Right? That's the first thing to realize in this question. Okay, so ETC, the HCN, the hydrogen cyanide, basically blocks the movement of H plus into intermembrane space. Right? You cannot pump the H plus over. So this is the intermembrane space. Okay. If you can't pump the H plus, that means you have less H plus, right? If you have less H plus, is it higher pH or lower pH?
Higher pH.
That's right. That's the answer. Okay. Do you understand that? We are not allowing H plus to go into the intermembrane space. You end up having less H plus, which means higher pH, right? Okay. Please be careful when you read the question on the test. Right? This one asks for intermembrane space. On the test, it might ask you about the matrix. Right? It depends which version you get, right? Okay. Like on the quiz number 2. Some of you had the question asking about hot environment. Some of you have it asking cold environment. All right. In class, I think in class we did cold environment, right? So a lot of you put the cold environment answer in the question. I mean, as the answer, even though it was asking you for hot environment. All right. So don't just assume it's the same question. It's the same type of question, but you got to read it carefully. Okay. Finally, just a couple more slides to go. This is talking about what is this talking about? This is talking about anaerobic respiration. All right. So majority of the time we do aerobic respiration. Okay, that's when you have adequate supply of oxygen. Okay, but when we don't, our body switches to anaerobic respiration for a little bit of time. Okay, to sustain ATP production. Some organisms, all they do is anaerobic respiration. Okay, they don't have the complicated organelles. They don't have the mitochondria to help them do the Krebs cycle and stuff like that. And then they just do anaerobic respiration. Okay, so what anaerobic means is without oxygen. Okay, so we can use anaerobic processes from yeast, for example, to make bread, to make alcoholic drinks. So let's take a look at the human case. And so in humans, when we exert ourselves physically beyond our normal capabilities, there's going to be a point where you don't have enough oxygen going into the muscle. Okay, just imagine running at full speed, right, as fast as you can. How long do you think you can sustain that? Okay, even if you're really fit, right, you won't be able to run at full speed for very long, right? Okay, so for the average individual, let's say you run at full speed, you might be able to keep that up for like 1 or 2 minutes, right? After that, you will feel the burn in your legs, right? That's the signal that tells you we don't have enough oxygen going to the muscle, okay? We don't have enough ATP to keep this going, okay? But I will try to keep it on for a little longer by switching to fermentation. So when oxygen used in the muscle exceed the rate of supply, the muscle switches to lactic acid fermentation. Okay. So let's go back to the situation again to understand this. When you don't have enough oxygen, I told you already that ETC clogs up and you are not making enough ATP, right? But more importantly, when the ETC clogs up, the NADH doesn't know where to go, right? It cannot let the passenger off. It cannot let the electron off, okay? So what do? Well, we gotta take the electron somewhere, right? So by switching to lactic acid fermentation, we provide an alternate destination for the electron to get off. Okay, so the NAD plus the NADH, instead of taking it to the ETC, they would just give the electron back to the pyruvate, okay, and then let it become something called lactate. Right, so by doing this, we regenerate NAD plus, and at least we can keep glycolysis going for the time being. Right, so you will still get 2 ATP. It's not a lot, That's why you cannot do lactic acid fermentation forever. It will just allow you to sustain it a little longer. So that's basically what's going on here. We have the glucose, glycolysis breaks it down into pyruvate, and then if we don't have enough oxygen, we cannot go to the step 2, step 3, and step 4. Instead, we convert it into lactic acid, and then we regenerate the NAD+. So the buildup of lactic acid is part of the reasons why, after like an intense workout, your muscle hurts, right? For the next couple of days, right? Your body needs to, slowly break down all those lactic acid that built up. Okay, so that's how lactic acid fermentation. For some microorganisms like yeast, okay, if you bake bread at home, you have to add yeast to it to make it rise. We also use yeast to produce ethanol. Ethanol is the drinking alcohol. There are different kinds of alcohol, right? Rubbing alcohol, the one that you get from like a drugstore, that is propanol, isopropanol. You can't drink that. Okay, that's poisonous to the body. The only drinkable alcohol is ethanol. There's also methanol, right? The one that you can rub on yourself when like to alleviate muscle pain, right? That's also not drinkable. Okay, so ethanol is the consumable alcohol, and we can use the yeast to produce alcoholic drinks like that because they use what's called alcoholic fermentation. So for them, they don't have the mechanisms to undergo Krebs cycle and etc. Is ethanol also gas? Okay, gas is like the one from the gas station. That's octane. Okay, so that's not an alcohol, but some cars can run on ethanol, their engine. Like theoretically, you can pour ethanol into the car engine and it will still burn. It might, destroy your engine over time because it's not designed to run on that. But it's a fuel that you can burn. Yes. I think some station, some brand of gas station, they say they add ethanol to it to winterize the oil or something. So I think that also exists.
Ethanol E85, I think is what it's called.
Is it E85? Yeah.
Yeah, it's made out of corn.
Oh yeah, the biofuel, right? Yeah.
Yes.
And it's the same process because when you basically ferment the corn, like the parts that we don't eat, right? I guess it's the, what do you call it? The skin, the cob. No, the I don't know what you call it. Like
The cob,
the,
yeah.
yeah, the cob and the skin part, right? When you ferment those parts, right? It basically generates ethanol, right, as well as a bit of carbon dioxide. Okay, so when the husk, that's right, that's right, the husk. Thank you. So the carbon dioxide is not what we are interested in when we make alcohol. That's the part that we want when you make bread. And then the ethanol, like I said, it's when you make alcoholic drinks. We do not do alcoholic fermentation, okay? Because ethanol is poisonous to our cells, actually. We do lactic acid fermentation. Okay, so this is the yeast. They can remain dormant. Like I have some in my fridge, okay? And then when I bake, I add them, they get reactivated, right? They do metabolism when they're reactivated, and then they create carbon dioxide, and that's what makes the dough rise. You don't have to memorize the step. This is just to show you, the difference between alcoholic fermentation and lactic acid fermentation. So basically, there are 3 fates of pyruvate produced by glycolysis. Okay? What we spend like a whole class talking about, that's the aerobic oxidation. Okay. Like I know these look very complicated, but it's basically the pyruvate gets converted into acetyl-CoA, remember? By removing a carbon dioxide, right? Releasing electrons that are going to be captured. And then there is the coenzyme A that re-energizes it. And then that goes on to the Krebs cycle as well as etc, right? So that's the normal path, the main path for humans and animals in general. When we exert harder than we normally could, right, running at full speed, like I said, then we will switch to lactic acid fermentation. But this is not sustainable. This is only going to keep you going for a little longer. Okay. Another example is like you try to hang on to a bar, okay, for as long as you can. Okay. After a while, you get tired. Okay. You mentally try to hang on, a few seconds longer. That extra few seconds when you're feeling the burn just before you let go, that's your muscle switching to lactic acid fermentation. Right? It's only pumping out 2 ATP at a time. Right? It will only keep you going a little longer, and then eventually you have to let go. For yeast and other microorganisms, they don't have mitochondria. They don't need to. They are very small. They don't need as many ATP as we do. So they will permanently be using alcoholic fermentation. All right, and that's it. Congratulations. You finished half of the course. Can you believe it? Okay, we're done lecture 1 and 1 to 5. So the first test is going to be next Thursday, which is 1, 2, 3, 4, 5 plus the lab. We will do a review on Tuesday. I will post the review sheet on eCentennial later today. So review on Tuesday, no class on Thursday. You just do the test. And then you will have your engagement week, which is reading week, and you have nothing, absolutely nothing due for my course after engagement week. All right. So
Sir,
yep.
if what's going on? If any